Good morning, everybody. I'm Paolo Franceschi, and I'm going to present the work Learning Human Motion Intention for a Physical Human-Robot Interactive Assistive Controller. The main motivation behind this work is to allow a robot to understand the desired human motion intention. We define with human intention the desired trajectory that the human wants to follow over a finite rolling prediction horizon, while in physical contact with the robot. To summarize, the method involves two main components: a cooperative game-theoretic controller and the integration of a model to predict the human intention, necessary for the correct implementation of the control framework. This work focuses mainly on the predictive model and its training, based on two separate steps. Let me give you a very brief overview of the cooperative controller and its main modules. The game-theoretic controller is composed of a motion planner, which gives the reference trajectory, and the predictive model in the green box, which predicts the desired human motion. The two references, which are typically different, are weighted according to the cooperative game-theoretic solution, and the proper robot control input is fed into a Cartesian impedance control. Let's now focus on the implementation and training of the predictive model. The predictive model is composed of recurrent neural network layers, in particular long short-term memory cells, cascaded with the standard fully connected layers. It takes as input data collected in time instants before the current one, and it predicts over a finite rolling horizon the desired human trajectory. To train the model, we propose an iterative training procedure. This is because, at the first iteration, no predictive model exists. Therefore, we initially start by collecting data with a control framework that does not use any prediction. Moreover, we record such data under precise conditions, which are a precise set of nominal trajectories available for the robot, a single user performing data acquisition, and that the user grasps the robot at its tips, right after the force sensor. After the first data collection, we have an initial dataset D0. With D0, we can make a first training. After obtaining a first predictive model M0, we can now plug it into the control framework and make predictions. So we can collect new data, and with the updated control framework, we can create a new dataset D1. We can train again with the D1. So now it's considered the predictive model. By iterating such a procedure, we will generate at each time a model MK that will be more precise in the prediction with respect to its predecessor. We can collect new data, we can generate a new dataset, dk plus 1, we can train over and over until convergence. In the end, we will have a final model that can be used in the control framework. Such a procedure has the great advantage that it improves the predicting capabilities of the model at each iteration, of the cost of long training time, and that the model is fitted on precise conditions. To overcome these issues, we propose transfer learning to quickly adapt the model. Transfer learning requires some more data collection. The new dataset required is very small compared to the previous one, and it can address different scenarios, such as different trajectories, different users, and different objects that have unknown inertia and different contact points. The quick data collection generates a new small dataset, DTL. The model can then be updated by training online only the last layers. Indeed, in the new training, we keep frozen the LSTM layers and update only the fully connected parameters. This makes the training way faster than training the full model. In the end, we have an updated model with the transfer learning, MTL. By plugging it into the control framework, the assistive controller now can handle new situations. Let's now see some results. On the left, it is visible the data acquisition procedure. The human grasps the robot at the tips and together move toward the target, shown in the monitor behind the robot. A red box appears randomly along the nominal path, and the human applies a force to deviate and avoid touching it. On the right, there is the prediction of the trajectory executed in 4 different iterations for a linear motion, visible below. The initial dataset is collected with 3 different trajectories: the linear trajectory of the previous slide and the 2 visible here. Again, predictive results for 4 iterations are given in this slide. After that, we tested the transfer learning procedure on new users, on new trajectories, and on different objects. Thank you for your attention. Should you have any questions, please contact me by email.